here we go with 14.3. So these are slides that we did in class together. So we're going to go through them quickly here. And if you feel like you already understand them, you are welcome to skip them and go to the part about ideal gases. So the idea behind the ideal gas law is that you can calculate any of these four parameters. So again, we're not limited to just pressure, volume, and temperature like we were before. We also now have moles. That's one difference between this and the gas laws. And the other thing being that there's no before and after. There's no subscripts 1, 2, blah, blah, blah. You actually can figure out, given three of these parameters, you can figure out the fourth one because we have this new constant here called R, which numerically relates all of these to each other. So we no longer have to use proportions. Okay, so R comes in a couple different forms. And one way that we can think about that is we can try to calculate the units of R by remembering the standard molar volume, which is the fact that at STP, 1 mole of gas occupies 22.41 liters per mole. So for example, we can say at STP, so remember standard pressure is 1 atmosphere. So we're going to say 1 atmosphere. I'll plug in units just so you can see them, but generally we don't because it's confusing to have so many units all together. 22.4 liters is the volume of this gas under those conditions, any gas. It would be 1 mole. And the temperature would be, the standard temperature is 0 degrees Celsius, which would be 273 degrees Kelvin. Some of you like to add 0.15 there just to be more specific, but you absolutely don't have to do that. Okay, what you'll find when you do this is the answer is 0.0821, and the units will be atmospheres, liters per mole K, which is really hairy, but that's just what it is. So this would be one of the possible values of R. Okay, and those will always be given to you. How could we find a value of R that corresponds to a different unit for pressure? We would plug in a different pressure here. So you may remember that 1 atmosphere is also 760 millimeters of mercury, and it is also 101.3 kPa. Maybe I should write equals there, huh? Okay, but importantly, you'll always be given the values of R. It's just kind of nice to know where they come from. Okay, so here's another possible value of R, and one thing that we talked about in class was you can actually relate one R to another R just based on this because the other things in it are all the same. So for example, you could say 8.314, and this is just, again, another way to relate all the different R's to each other to convince you that they are related and they're all kind of derivations of each other. Okay, if we're trying to convert kPa to atmospheres, the only thing we want to do here is cancel kPa. So we need to have kPa down here, and we're trying to convert it to atmospheres, so we have atmospheres up here. And if you were to do this, you would get the number we found on the previous slide, 0.0821. Okay, and if you did it again with millimeters of mercury, you would get 62.4. Okay, and this point here is what we did on the previous slide. So the most important thing with R is you want to always be careful which R you pick when you're doing calculations, because it needs to match the pressure units that you use. So if you're going to plug in a pressure of 1 atmosphere, you don't want to use 62.4 because that corresponds to millimeters of mercury, so you have to be careful of that. Okay, so let's do an example. Samantha goes camping and wants to inflate her air mattress. If she wants to put 20 liters of gas in the mattress at a temperature of 17 degrees Celsius and an atmospheric pressure of 101.3 kPa, how many moles of gas does she need? There's two ways you can do this mathematically. Some people prefer to write out the law and then solve for the unknown right away, which I don't really particularly like to do, but you're welcome to. Some people also, and I do recommend this if you feel overwhelmed by the amount of writing here, to pull out the numbers and identify them. Like 20 liters, what is that? That is our volume. Okay, 17 degrees Celsius, what is that? That is our temperature, and we always convert those to Kelvin immediately because Celsius is not helpful here. Okay, I'm going to include the dot, so that's 0 significant. Okay, and then the temperature or the pressure is 101.3 kPa. So once you get used to these, this step won't feel as important, but initially if you're feeling overwhelmed by the number of variables, it might be helpful. Okay, we're going to plug in. I don't include units in the numbers here because I think it makes it more confusing looking, but you can. Okay, our unknown is N. Our R, we want to pick the R that corresponds to our pressure unit, which in this case is kPa. So we're going to pick this R, 8.314, and then we're going to multiply by our temperature, which was in Kelvin 290. Most of these numbers have 3 sig figs at any rate. The one with the fewest has 3 sig figs. So we will get, I hope this is what we got in class. That number seems a little weird to me, but we're just going to go with it. 0.84. Oh, that makes sense. Okay, so one way you can ask yourself if it makes sense is to remember when we need 3 sig figs, because we have 3 here. 4, 3, 4. Remember that this is about standard temperature and pressure, and at about standard temperature and pressure, 1 mole of gas will be 22 liters, and this is a little bit less than that, so it makes sense that it's a little less than a mole. I feel like this air mattress is going to be too small for her. Maybe she's a mouse. Okay, so here we have a weather balloon with 2.51 moles of helium at 20 degrees Celsius and 94 kPa. Same thing, pull out the numbers and identify them. 2.51 moles. Temperature is 20 degrees Celsius. We're going to add 273 right away. If you want to conserve that 0 being a significant figure, then you can add this, 0.15, rounding up to 0.2, and then you'll get 293.2 Kelvin. And the last thing is our pressure, 94.0 kPa. Okay, again, filling in the same way we did before, except in this case we're looking for volume. Okay, 94.0 times volume gives us 2.51. This is called plug and chug. We're going to use the same R because we're still using kPa. We're going to use our temperature in Kelvin always, and we will get something real quick here. My trusty TI-83. Okay, I got 65.1. If that's wrong, and you've double checked it, then you're probably right. Okay. So this is assuming that these are all ideal gases, and we've made some assumptions in our kinetic molecular theory about ideal gases. Remember, we assume that they don't have any IMFs. We assume they don't have any volume. We also assume their collisions are perfectly elastic and that they're moving constantly and quickly and randomly. Do they actually exist? No. How could they, right? Because everything attracts everything else, at least with London dispersion forces, and all particles have volume. You can't have an atom that doesn't have any volume, so they don't actually exist. But is it a good approximation? What do you think? Yes, it is a pretty good approximation most of the time. Okay. So, yeah, based on what you know about ideal gases, what would be true of real gases? Like, in what way do real gases differ from ideal gases? Well, they have IMFs, and again, everything is technically a real gas, and they have particle volume. Okay, so then based on this, we want to ask ourselves, under what conditions would gases behave most ideally? So I'm going to draw your attention to a phase diagram for this. And you remember phase diagrams, we can just do water, but a lot of them look kind of like this. And you remember this is liquids, this is solids, this is gases. Do you remember what the y-axis represents? Pressure, temp. Okay, so if we wanted to ask ourselves on what part of this graph are gases the most gas-like and the least like liquids, it's not really up here because this is pretty close to liquids. It's not down here, it's pretty close to solids. It's like this teeny corner over here is as far from the other stuff as possible, okay? And that represents super high temps and super low pressures. Okay, so gases behave most ideally at high temp and low pressure. Okay, another way that we can think about this is in terms of these two parameters. So under what conditions do the IMFs start to become more significant? If you think about a gas, let's see, IMFs become more significant think about a gas, how the particles are zooming past each other. Remember our trusty magnet demo where you like move them past each other really fast, nothing happens, but if you slow the magnets down, they have time to kind of click together. So what's the equivalent for that with the gases? It is slowing them down is cooling them down, right? Kinetic energy. So IMFs become more significant at low temp to the point that they actually literally become a liquid and no longer are a gas if the temperature becomes low enough. So that's why high temp, which is the opposite, is where it's more ideal. Okay, another factor, the particle volume, when does that matter? So if you think about like a really low density container here, and you have like particles in it, and they're kind of spread out. Let's say that you were able to take all of those particles and condense them into one little corner, which you could do by making them a liquid. Okay, so let's say that it has that little tiny volume. The particles themselves occupy that little volume. So we would say at low density, the volume of the particles is a really low portion of the total volume. To the point that you could consider it negligible, right? So basically negligible. Negligible. Okay, what happens if you push in on the sides of this container so that the container only has this volume now? You notice how this is like a quarter of this. So once you compress a gas to a high enough pressure, it eventually becomes a liquid. I think you saw that in the demo video with the butane lighter. The butane in the lighter is actually a liquid, and it becomes a gas when it enters a lower pressure area. So if the pressure gets high enough, the particle volume is no longer negligible. Or you could say no longer, if you have more space than me, no longer a negligible portion of the total volume. No longer a negligible portion of the total volume. Okay, which is why, if again, we're going back to ideal behavior, you want super low pressure, huge containers with little tiny amounts of particles in it. Okay, onwards. Okay, we're always going to assume ideal behavior. There's actually a version of the ideal gas law that takes into account the particles, IMFs, and their volume. And sometimes the ideal gas law is incredibly inadequate to describe certain gases under certain conditions. But if you think about particles, like try to imagine the substance or the particular gas that would have really low IMFs and really low particle volume. So hydrogen or helium would be pretty ideal if we're talking about gas identities for pretty ideal gases, and then these are ideal conditions, which is kind of a different question. Couple slides of 14.4 to get us ready for class on Thursday. These will be quick. If you have a mixture of gases like air, because all of the particles in that mixture are colliding with each other and with the container walls, if it's a container, they all contribute to the pressure. But it makes sense that if the mixture has like a ton of nitrogen, for example, like air, and a little bit of oxygen and a little tiny bit of argon and carbon dioxide, that most of the pressure will be due to the thing that you have more of and less of the pressure, but still some of the pressure will be due to the things that you have less of. So that's kind of the spirit of this part of the lesson. Okay, one other thing that can be present in air but isn't always is water vapor. And what do you think that they would determine how much water vapor there was? Lizzie? Humidity. Good. Middle school science. Thank you, Ms. Tyson. Okay, So Dalton's law of partial pressures basically says that if you have a mixture of gases, O2, N2, H2O, CO2, argon, whatever, and you put them together, each of them has their own individual pressure, which is called a partial pressure, okay? And if you add up each of their partial pressures, it will give you the total pressure of that mixture. Okay, so for example, if you have a sample of air and the partial pressure of the nitrogen is 0.78 atmospheres, and the partial pressure of the O2 is 0.20 atmospheres, and the partial pressure of the H2O is 0.01 atmospheres, and maybe the partial pressure of the CO2 is 0.001, and sig figs, that basically doesn't count. Then you would say that the total pressure of that mixture is, it's going to be good, 0.99, and the this one would disappear, sig figs wise, okay? You'd say 0.99 atmospheres. So that's the essentially what Dalton's law is saying. Okay, so another example would be like Mr. Johnson, our friend from the video. Let's say he has this bin. He's collecting gas over water. Let's say in this case he's collecting hydrogen. Okay, maybe there's some kind of reaction happening here, like a metal reacting with acid and it's bubbling up. Okay, and he's collecting that sample. The assumption that we made on Monday was that that sample is pure hydrogen. Okay, but what we know now, or what we're talking about now, is that there's actually a little bit of water that's also evaporated into that space. So while the majority of that sample is hydrogen, a small portion of it is also water. So it makes sense then, and we mean water vapor, very specifically, water vapor, okay? And so it has a certain amount of vapor pressure. That's the water vapor causing pressure. So it makes sense then to say that the total pressure in that space up there is due to not only the partial pressure of the hydrogen, but also the partial pressure of the water vapor. So the example that we have here is maybe the outside pressure is 760 millimeters of mercury. So like the pressure here is 760, so the pressure there must be 760, like in your lab. But in the lab, we assumed, if this pressure is 760, then this pressure of the butane is 760. But what we're talking about now is that the total pressure of the mixture is 760, and we're told that the vapor pressure of the water is actually 20. So we need to take that into account. So we're basically using this equation down here and plugging in numbers over here. Okay, so 760 will be the pressure due to the H2 and the pressure due to the water. And with the easiest math of your life, you will find that the pressure due to the hydrogen is 740 millimeters of mercury, which is almost what we had before, but slightly lower, because what we were not taking into account is that some of this pressure in this space was caused by the evaporated water. Then we had to pull that out in order to actually find the pressure from just the hydrogen. Okay, one concept that's going to be useful to us in doing these calculations is mole fraction. And mole fraction, you might want to think of it as just like percents in decimal form. So for example, 50% is 0.5 as a decimal, right? That's basically what mole fraction is. So it's what the portion of the thing you're looking at divided by the total, but not times 100. For example, when we say in class, what percent of this class is boys, you might say 8 divided by 18 times 100. It's just going to be 8 divided by 18. That's the fraction. And in this case, when we're talking about mole fraction, it's going to be in terms of moles. So the symbol for mole fraction is a capital X, which makes it look confusing, but it's not confusing. So it'd be the moles of A divided by the total moles. And if there's two things, it'd be moles of A and moles of B, but there might be more than that. There might be 3 things, there might be more. Okay, and it's not times 100. Okay, as an example, air is about 20% oxygen. So, so one more thing that this is useful for, let's say this is the mole fraction of A, is, we'll do lots of examples of this in class, but basically, if the mole fraction of something is 0.5, that means that it, in addition to being half of the moles of the mixture, it also is responsible for half of the pressure of that mixture. So if the total mixture has a pressure of 1 atmosphere and half of it is N2, the pressure of the N2 will be 0.5. atmospheres. So the equation, and this will make more sense as you use it, the equation for the pressure caused by some gas A, it's a partial pressure, the partial pressure of A will be basically the total pressure, but you're going to multiply it by the mole fraction of A. We'll do more examples of that in class, I promise. Okay, here's another example, or here's a example. So air is 20% oxygen. So we're being told from this that the mole fraction of air, oh, just kidding, the mole fraction of oxygen is 0.2. Remember, up here, it's like percent in decimal form, okay? And then it says, what is the partial pressure of oxygen? So if you look at this equation up here, and it says the total pressure is 740. So we're going to say the partial pressure of oxygen will be equal to the total pressure times the mole fraction of oxygen. When we plug in our numbers, what is the partial pressure of oxygen? Well, the total pressure is 740. If I multiply that by 0.2, or in other words, if I take 20% of it, I will find the partial pressure of the oxygen. And in this case, I wish I could do that in my head quickly, it is 148. Sig figs, I guess we have to round. That's kind of annoying. 150 millimeters of mercury is the partial pressure of the oxygen in this example, and we will do more examples in class.